Hi folks, Dr. Rutner here. This is the video walkthrough looking at the hypothesis testing procedure when we are comparing two different proportions. And so we're going to take a look at this process, how we formulate hypotheses, how we do the computations, and then we'll walk through all the steps for a problem. So in this case, what we're looking at is comparing two population proportions. You can see that illustrated here is pi1 minus pi2. We're interested in the difference between those. Remember that a proportion is looking at how many items out of a sample meet some characteristic of interest for us. In order to use this test, we need to verify that our sample size taken in combination with the proportion is large enough so that we can rely on having a normal sampling distribution for the difference between proportions. And so there's four relationships that we need to look at to verify that. For each of the two samples that we're working with, we're going to look at the sample size times the proportion and sample size times 1 minus the proportion and verify that those values are greater than 5. Do that for each of the two samples in order to support this assumption. Then the point estimate that we will be using to evaluate our hypotheses is going to be the difference between our two sample proportions. And so we have that illustrated as P1 minus P2 here. All right, so that's the basic underlying idea. Let's take a look at hypotheses that we can set up. And hopefully by this time, it's not terribly surprising to see that we could create a one-tailed hypothesis where our region of rejection is either in the lower tail or the upper tail of the distribution. And so taking a look at the null hypothesis here, with a lower-tailed test, we're hypothesizing that the difference between population proportions is greater than or equal to 0, which gives us an alternative of less than 0 for that difference. With a lower-tailed test, our entire alpha value goes in the lower tail of the distribution. That gives us a negative critical value of z, and so we'll formulate our rejection rule accordingly. So we'll reject the null hypothesis if our test statistic is less than that negative critical value of z. If we do an upper-tailed test, doing basically the same thing, we just reverse all the signs. So our null hypothesis is less than or equal to, our alternative hypothesis is greater than. We put our rejection region in the upper tail of the distribution, and we get a positive critical value of z. And so we would be rejecting the null hypothesis if our test statistic winds up being up there in that rejection region or greater than the critical value of z. Then for a two-tailed test, what we're hypothesizing here is that the difference between the two population proportions is 0, with an alternative being that it's not equal to 0. That causes us to split our alpha value into 2 and put half of that alpha value in each tail of the distribution. We get two different critical values of z, a positive and a negative value, and we are going to reject our null hypothesis if our test statistic is either greater than the negative value or less than the negative value or greater than the positive value. So that's our hypotheses. Now, the other thing you'll probably note here is we're working with z values instead of t values. And the reason for that is I'm going to back up one slide here. If we pass these tests, if we have a large enough sample size in relation to our proportion that we're working with, then we are using the normal distribution. We're assuming that the sampling distribution of the difference between proportions follows a normal distribution. So just as we did with one sample hypothesis tests and with confidence intervals for the proportion, we're working with a normal distribution instead of a t-distribution here. All right, so got an idea of the kinds of hypotheses. Let's take a look at some of our computations. Now, actually, before I go to the next slide, I do just want to point out one thing so it's fresh in your mind. Remember that we're following the standard procedure of making sure that a statement of equality occurs in each of the null hypotheses, and that's true regardless of whether we're doing a two-tailed test, where that's really what we're hypothesizing, is that the difference is equal to 0, or a one-tailed test, where we're hypothesizing greater than or equal to, less than or equal to. In all three of those situations, the condition of equality forms at least a portion of what we're stating in our null hypothesis. So that condition of equality is a part of that null that we assume to be true unless we can overturn it. Now, the reason I point that out here is because if we go to the next slide, what that lets us do is to simplify some of the computations that we need to do for our test statistic. So if we're assuming that those two population proportions are equal to one another, then that allows us to compute a pooled estimate for the overall proportion based on our sample data. And so this pooled estimate, we're referring to it with the symbol P bar. So that's kind of like X bar that we've looked at before, or D bar that we looked at when we were doing the paired t-test situation. P bar is an estimate of the proportion pooled across or overall our different samples. And we compute that by taking the two different X values, where X is the number of items of interest in a sample, summing those together across our two different samples, and then dividing by the sum of the sample sizes. So just an overall proportion across both of our samples. All right, so keep that in mind. We've got our pooled estimate of the proportion. And with that, we can take a look at how we compute our Z statistic, our test statistic. And I think this follows a pattern that is fairly familiar to you now. We are taking our sample value. In this case, our sample value is the difference between the two sample proportions. We subtract our hypothesized population value, in this case, the difference between population proportions, and then we're going to divide by a standard error in order to get our Z statistic. We've kind of probably seen the biggest differences from one technique to another in the standard error, and I don't think this one is any exception to that. So here what we're doing for our standard error is we're taking that pooled estimate of the proportion, that P bar that we just looked at, multiplying that times 1 minus P bar, and then multiplying by 1 over sample size 1 plus 1 over sample size 2. Get that product, take the square root of the whole thing, and that becomes that's how we compute the standard error for this distribution. And just in case you needed to refresh your memory on any of those subordinate computations, they're down here at the bottom of the screen. So we're going to compute a Z statistic, compare that to a critical value of Z that we determine based on our chosen level of alpha, and that's how we're going to evaluate our hypotheses. All right, so let's take a look at a problem, and we are working with proportions. Can't do a proportion problem without taking a look at a polling question, right? It's a pretty classic example. So we've got some campaign polling going on here, and early on in the election campaign, we polled 800 people, found that 460 out of those 800 favored the candidate that we're looking at. Maybe that's our candidate, and maybe this is internal polling, I don't know. And then later on, just before election day, we did another poll. And this time we polled 1,000 people, found that 520 of them favored our candidate. And so the question that we're trying to address here is, at the 1% level of significance, is there enough evidence to say that our candidate's popularity has changed? Now, since we're looking at a question where we're evaluating whether a proportion has changed, that's going to be a two-tailed hypothesis test. Change could go either in the positive direction or in the negative direction. If this question had been stated a little bit differently, for example, if it had said, is there sufficient evidence that the candidate's popularity has increased, then we would be looking at a one-tailed test. Or if it had said, is there evidence that the candidate's popularity has decreased, we'd be looking at a one-tailed test. But in this case, it says, is there evidence that the candidate's popularity has changed? We could also say, is there evidence of a difference between candidates' popularity over the two polls? But both of those different types of wordings lead us to a two-tailed test. All right, so kind of got that in mind now. Let's go ahead and I'm going to go to my write-up. And as I did with the other examples that we looked at, I'm going to post this write-up out to Blackboard for you so you can get a copy and take a closer look at these computations. We're testing at the 1% level of significance, and we're going to do that test three ways. We're going to look at the critical value approach. We're going to compute the p-value, see if that confirms what we determined with the critical value approach, and then compute the 99% confidence interval, and we should see that that confirms what we did as well. So that's kind of the overall that we're going to look at here. Let's take a look at our hypotheses. We are hypothesizing that the difference between population proportions, and in this case the populations, just to put this in context, the populations would really be how many people favored our candidate at the time we did the first poll, and then how many people favor our candidate at the time we did the second poll. We are going to evaluate that based on our surveys, based on our individual polls that we did of the registered voters. All right, so in this case, I've got pi1, I guess, is going to be the first call, pi2 is the second call. All right, I couldn't really come up with a better way to do subscripts for this one, so I'm just using 1 and 2. All right, so our null and alternative hypotheses there, and then gathering together our information, testing at alpha 0.01, and for the first poll, 460 out of 800, for the second one, 520 out of 1,000. Then easiest way to actually evaluate our sample size assumptions in this case, and it's because we're given these raw numbers to work with here, is to look at x1, which is 460, and 1 minus x1, which is 800 minus 460. Both of those are greater than 5. Same thing is true for the second sample, 520 and 1,000 minus 520, both greater than 5. So we have a normal sampling distribution of the difference between proportions. So we can use our hypothesis testing technique. For our critical value of z, well, our alpha value that we're using is 0.01. So half of 0.01 is 0.005, and that gives us a critical value of z of 2.578. So we're splitting that alpha in half, and so we get plus and minus critical values from our symmetric distribution. We're going to reject our null hypothesis if our test statistic is less than minus 2.578 or greater than positive 2.578. I didn't state them here, but we could also state our rejection rule in terms of the p-value, and that would be that we would reject the null hypothesis if our p-value is less than alpha, or in terms of the confidence interval, and in that case we would reject the null hypothesis if the hypothesized population or difference between population proportions falls outside of the confidence interval that we determine. All right, now before we get too deep into our computations, let's go to our spreadsheet and let's just verify those critical values of z and see where they came from. So in my spreadsheet, what I've got here is we're hypothesizing a population proportion difference of 0. We're testing at the 0.01 level of significance. And then I have my given data for the early poll and for the late poll. So just kind of collecting that data here. I'm going to come down here to where I'm doing my critical values. And we can determine those critical values with our inverse function for the normal distribution. Remember, an inverse function is what we use when we are starting with a probability, and alpha represents a probability, starting with a probability, and we want to find a z-score or a t-score to go along with it. So in this case, I want to find the probability for my lower critical value for 1/2 of my alpha value. So I'll take alpha and then just divide by 2 right here in the argument. And that gives me my lower critical value of minus 2.578. And then for the upper critical value, I want half of the alpha value in the upper tail of the distribution. That gives me a cumulative probability for everything else of 1 minus half that alpha. And so again, I'm using my norm S inverse function. And so what I will put here is 1 minus 1/2 of the alpha value, and that gives me my positive 2.578. So just confirming that we're able to determine those critical values. And of course, if you want to, you can also look those up in the table and confirm them as well. All right, so let's go back here to my computations. And I've got those computations written out, and we'll catch them up on the spreadsheet here in just a moment. So we're going to compute our two individual group proportions as well as our pooled proportion. Let's see, I tell you what, let's do the side-by-side thing here. And I'm going to adjust so we can see our formulas as we're going. Just so I think it helps to be able to look at the formula we're trying to create while we're building it in Excel. Now, for our group 1 proportion, that's actually easy enough, so I don't have a formula written out. We're just taking the number of people who favored our candidate, dividing by the total number of people that we called, and do the same thing for group 2. So that'll be 520 out of 1,000 for group 2. And just, kind of stepping back and looking, we do notice that even though the number of people who approved our candidate went up from poll 1 to poll 2, from the early poll to the late poll, the proportion went down because we were surveying a larger number of people in the second poll. So went from 0.575 to 0.52 for the proportion. So we can observe a difference. Of course, we have to complete our hypothesis test to determine whether that difference is statistically significant or not. All right. And then I'm going to go ahead and compute, since I know I'm going to need this when I compute my test statistic, I'm going to go ahead and compute the difference between my sample proportions. And so that'll be the 0.575 minus the 0.92. That's a difference of 5.5%, or 5.5 percentage points, I guess I should say. All right, then for my pooled estimate, I'm going to take the sum of the people who favored my candidate in the two polls, divide by the sum of the total number of people we surveyed in the two polls. And so that's going to be the 460 plus the 520. And then I'm going to divide by the 800 plus the 1,000. And so that gives me a pooled estimate across the two samples of 0.544. And just as a reasonableness check, we can see that that number falls in between the two proportions, and you would expect that it should fall in between the two proportions. All right. Next thing I'm going to compute, I'm going to kind of scroll down in the Word document here just a little bit so we can see everything. The next thing I'm going to compute is the standard error that's going to be the denominator of this computation for my test statistic. So that's going to be p bar times 1 minus p bar times 1 over sample size 1 plus 1 over sample size 2. Make that computation, take the square root of the whole thing, and that'll be the number that goes in the denominator of this computation. So we can do that kind of all at once, especially since we've got our p-bar computed, our pooled estimate. So p-bar is here in cell B18. Multiply that times 1 minus the p-bar, and then multiply that times 1 divided by sample size of from the first poll, plus 1 divided by the sample size from the second poll. Close the parentheses on that computation, and then close the parentheses on the square root function. So that gives me a standard error of 0.0236. Now that number doesn't show up here. I actually showed out the computations, plugged the p-bar and the sample sizes into the computations, but that's if I were to resolve just that value in the denominator, it should come out to 0.0236. Let's go ahead and compute our total test statistic. And I'm going to compute that by taking my difference between the sample proportions. I'll subtract the hypothesized difference between the population proportions, and then divide by that standard error. So that gives me a test statistic of 2.3282, and I do have that number written down on the document here. And of course, I do suggest you verify those computations yourself, just to make sure that you can do them and make sure that I haven't made any math errors here. All right, so there's my test statistic. Now, we'd already looked up our critical values or determined our critical values, and so based on that, we can make a decision. We are going to fail to reject our null hypothesis. 2.32 is not greater than my upper critical value, and it's certainly not less than my lower critical value. So we will not reject that null hypothesis. And I've got my managerial conclusion written out here. Let's make this so you can see it a little bit better. And so my managerial conclusion is that at the 0.01 level of significance, we do not have enough evidence to conclude that the proportion of voters favoring the candidate is different between the two surveys. So yes, we saw that it changed, but it did not change by enough to cause us to say that that change is statistically significant at the 0.01 level of significance. All right, so that's our conclusion by the critical value approach. Now let's also go ahead and compute our p-value. And before I go back to the spreadsheet, I'm just going to scroll down here and refresh your memory on what a p-value is and how we're doing this for a two-tailed test. A p-value, no matter whether we're doing one-tailed or two-tailed, a p-value is the probability that we get a test statistic at least as extreme as what we got if the null hypothesis is true. Now, because we're doing a two-tailed test, we need to consider that more extreme, at least as extreme, could go in either the positive or the negative direction. And so our p-value is going to be the probability of getting a test statistic that is less than minus 2.3282. Remember, that's the test statistic that we got was positive of that value. So we're going to take that probability of getting more extreme in the negative direction, add the probability of getting more extreme in the positive direction, and that's our total p-value. You can see how the computations work out here. So going more extreme in the positive and in the negative direction give us 0.00995. Sum those together to get the total p-value. All right, let's go back to our computation. And we're going to get that p-value. I'm actually going to build this formula kind of a piece at a time so you can see how it all works together. Now, what we're doing here to get this p-value or this probability is we're going from a z-score to a probability. So for that, we'll use our norm S dist function. Like I said, I'm going to kind of build this out a piece at a time just so you can see how it goes. So I'm just going to start with norm S dist, and I'm going to give it my test statistic and tell it that I want a cumulative probability. Okay, and so that gives me 0.9900 as the result. And what that represents is that is the cumulative probability, or in other words, everything to the left of the test statistic, the test value of z that I got, everything to the left of 2.3282. Now, that's not exactly what I want. What I really want is everything that is more extreme, not everything to the left. So the first thing I'm going to do is I'll do 1 minus, and that gives me a very big number. Let me adjust my formatting here because, or excuse me, a very small number with a lot of decimal places. I'm just going to adjust my formatting here because I don't want to look at all those decimal places. It gives me essentially, here, let's go back a couple more, 0.00995, which was the number that I had written on the document here. Sorry for the jumping back and forth, 0.00995. Then I need to multiply that by 2 because this just gives me one tail of my p-value. I need both tails. And so I'm going to come back into my formula here, and I'm going to say 2 times the result of 1 minus the probability to the left of my value of z. And that gives me my actual p-value of 0.0199. The other thing that I'm doing in this formula, and let me blow this up so you can see the whole thing, is just to make my formula so that it's flexible, so that it's going to work whether my z statistic here is either positive or negative. The other thing I'm doing is I'm taking the absolute value of that test statistic. And so that way I'm not going to break my function and my logic if if I were to use this same basic spreadsheet template and come up with a negative test statistic. So I'm going to just plug in that absolute value function. So what that's going to do is take the absolute value of my test statistic, use that as the t-value that we used, or the z-value for our norm s dist function. That gives me the cumulative value to the left of that, subtract that from 1, and then multiply it by 2. All right. And so 0.019900, I'm going to drop that back down to 4 decimal places, so 0.0199 is my p-value. Now, again, we can use that to make our rejection decision. So 0.0199 is not less than 0.01, and so that confirms my decision not to reject the null hypothesis. Okay, so we've done our p-value computation, and we've seen that that verifies the result that we got from the critical value test. Another nice thing with the p-value is we can use it to answer some other questions. So for example, just by looking at this p-value, if I wanted to know whether I would have rejected this null hypothesis had I been testing at the 0.05 level of significance instead of testing at 0.01, I don't have to go through and redo everything. I can just figure that out just by looking at my p-value. So if we had been testing it at the 0.05 level, I would have rejected this null hypothesis because the p-value that I got is less than that level of alpha. So that's the nice thing about a p-value, is it gives you a little bit more information in terms of how significant your test results, your sample results actually are. Now, in this case, like I say, we did not reject because 0.0199, the p-value we got, is not less than 0.01. But if we had increased that alpha value, we could have rejected this null hypothesis. All right, last thing I want to do is go ahead and look at our confidence interval. And this is actually a little bit different than what you've seen before. So let's go back to our slides here quickly. And here is the computation for our confidence interval. So what we're doing is we're taking, again, a point estimate for the value that we're estimating here. Our point estimate is the difference between our two sample proportions. And then we are going to add and subtract a margin of error. And our margin of error is going to be determined by taking z for half of our alpha value and multiplying by a standard error, but we're computing our standard error just a little bit differently here. So the standard error is going to be the proportion of the first sample times 1 minus the proportion of that sample over n1, the size of the first sample, plus the same thing for the second sample, proportion times 1 minus proportion over n2. So slightly different computation here. And so let's go back to our spreadsheet. And let me go ahead and get that formula showing in the Word document, because I think that's the one where we can see it the easiest. And so I want to go ahead and compute margin of error. And my margin of error is going to be the z-score that I've already looked up. And this is my critical value of z, times the square root of the term you see here. And I'm feeling fairly ambitious here. Let's see if we can't build this whole thing at once without making any little syntax mistakes. So I'm going to take my critical value times the square root of my first proportion, which is this group 1 proportion, times 1 minus that proportion, divided by my first sample size, which is the 800. And then we're going to add same computation for the other sample. And so that is my second proportion. I'm just coming down here so I can take a look at my formula. My second proportion times 1 minus that second proportion divided by the size of my second sample. And so then I will close that square root function. And so what that gives me is a margin of error of 0.0607. All right, then to compute our confidence interval limits, we're going to take the difference between our two proportions and subtract that margin of error, which gives us a lower limit of minus 0.0057, and we'll take that difference and we will add our margin of error, which gives us 0.1157. And those match. I'm going to blow up the Word document here for a second. Those match what we had computed and reported here in the Word document. So with 99% confidence, the true population difference, or the true difference between population proportions, is between minus 0.0057 and positive 0.1157. This confidence interval contains the hypothesized difference between the populations. And so once again, we confirm that our decision is we're going to fail to reject. We do not reject our null hypothesis. All right, so that wraps up our discussion of population proportions and hypothesis test when we're comparing two of them. The remainder of the walkthroughs will be in separate videos.